Magnetic effect of an electric current. Subtopics: magnetic effect around a current carrying conductor, electromagnets, force on a current carrying conductor, applications of magnetic effect of an electric current. Introduction. The relationship between electricity and magnetism has long been established, beginning with the work of early scientists such as Michael Faraday. This relationship is today applied in many areas such as industries, generation of electricity, magnetic picking, loading, and unloading. Magnetic effect around a current carrying conductor. Introduction. The magnetic effect around a current carrying conductor. Activity 4.1. To show the magnetic effect around a current carrying conductor. Play the video clip and observe the effect of holding a current carrying conductor near a plotting compass. Observation. When the switch is open and the plotting compass is placed below the wire, the needle deflects and tends to be perpendicular to the wire. More specifically, the compass needle points away from us. This direction reverses with the direction of current. This observation is evidence that a wire carrying an electric current sets up a magnetic field around itself. The direction of this field depends on the direction of current. The experiment with the compass needle may be repeated by placing the compass needle above the wire without changing the direction of current. In this animation, drag the compass needle to the position marked Y so that it is directly above the wire. Close the switch and observe the direction of the needle in relation to the current. What is the effect on the direction of the needle of the moving compass needle from below the wire to the top? Direction of magnetic field around a current carrying conductor. Activity 4.2. To determine the direction of a magnetic field around a current carrying conductor. Observe the alignment of the compass needles when cell A is inserted and again when it is replaced by cell B. Conclusion. From this experiment, the direction of magnetic field depends on the direction of current. This direction of the field can be predicted using the right hand grip rule, which may be stated as follows. If a conductor carrying an electric current is grasped using the right hand with the thumb pointing along the wire in the direction of current, the curled fingers will point in the direction of the magnetic field. Force on a current carrying conductor. Activity 4.4. Investigating force on a current carrying conductor. In the setup in figure 4.4, two stiff brass rods, X and Y, are mounted parallel to each other on a plastic or insulator support. Another brass rod, AB, is mounted across X and Y. A strong horseshoe magnet is placed such that AB is between the poles. Observe the effect on the rod AB of closing the switch, reducing current, or by increasing resistance, aligning the magnetic field with the rod, reversing the direction of current, and reversing the poles of the magnet. Observations. From the experiments, it is observed that the brass rod AB experiences a force and rolls along the rods XY when current flows through it, When either the direction of the field or current is reversed, the direction of movement of AB also changes. When the amount of current is increased, the rod moves faster. When magnetic field is aligned with rod AB, the rod remains at the same position. Conclusion. A conductor carrying current in a magnetic field experiences a force, and if the conductor is free to move, it does. The size of the force depends on the amount of current. The direction of the force depends on the direction of the magnetic field and the direction of the current. The force is stronger if a stronger magnet is used. The direction of force on the conductor can be predicted by Fleming's left-hand rule, which states as follows. If the left hand is held with the thumb, the first finger and the second fingers mutually at right angles, so that the first finger points in the direction of the magnetic field and the second finger in the direction of current, then the thumb points in the direction of motion. This rule is illustrated in figure 4.6. Applications of magnetic effect of electric current. Electric bell. Electric bell is one of the important common applications of magnetic effect of electric current. The figure shown represents an electric bell. To study the working of an electric bell, click the switch to close it and observe what happens. When the switch is closed, current flows. The soft iron core gets magnetized, attracts the soft iron armature. The following animation shows the motion of armature slowed down to reveal the making and breaking of contact during the working of an electric bell. Close the switch to operate the bell and observe the contact more closely. Explanation. When the switch is closed, current flows. The soft iron core gets magnetized and attracts the soft iron armature. The iron armature moves with the hammer, which then hits the gong. Meanwhile, this creates a gap at the contact X, causing the circuit to break. This causes current to stop flowing. The soft iron core loses its magnetism and releases the soft iron armature, which then springs back to remake contact and complete the circuit again. The process is repeated until the switch is opened. Electric motor. Electric motor is used in many devices such as electric drill, dryers, electric fan, and a host of other electric machines. Play the following video to observe a simple electric motor powered by dry cells. Conclusion. The speed of the rotation of the coil depends on the amount of current. The more the number of coils, the faster the speed of rotation of the coil. The stronger the magnet, the faster the speed of rotation. A change in the direction of the field affects the direction of the rotation of the coil.